Thank you. Yeah, thank you very much, CEAD, for the invitation. Very happy to kick off this series about applications of the CEAD systems. So my name is Joris. I'm a PhD researcher with geometrical research at ETH Zurich, and yeah, like mentioned, I'm investigating the possibilities of 3D printing in architecture, specifically looking into robotically 3D printed formwork for concrete structures. So concrete is the most used material in the world. It's actually, the only material that's used more is water in the world. So it's the most used construction material. So it has a massive impact on the planet, and it really accounted for the growth of our civilization, and it brought the built environment to where it is at this point actually. So you can see the amounts that are being produced. It's around 30 billion tons per year, and this vastly outnumbers, for example, the amount of steel that's being produced or the amount of timber that's used in the construction industry. That's also why it's no wonder that concrete has a big impact on the emissions, on the greenhouse gas emissions. So this is particular because of the production of cement. So in Europe, for example, cement is responsible for 5% of CO2 emissions. Whereas worldwide, it's actually 8% of CO2 emissions that are caused by cement. So very vast amounts. So if we want to transition to a more sustainable built environment, it's also very important we address this challenge. So there's already many people that have looked into strategies that we can use to reduce the carbon imprint of the construction industry, specifically in terms of concrete. And they found that we can actually reduce the amount of impact that the concrete has on the construction industry by around 70% by 2050, which would be a good path towards carbon neutrality as well. So how can we do that? So concrete, it's composed out of cement, or a binder that's usually cement, aggregates, and water. And on the first scale, you have basically the clinker, which is the base material for the cement. And what we can do here is we can have more efficient production processes, for example, using renewable resources. Then we can just put less clinker in our cement, and we can put less cement in our concrete. So all these three aspects, they have to do with the material. So material scientists are working very hard on creating more sustainable concretes that have a less carbon impact per cubic meter of concrete, for example. But on the other hand, what we can also do is use less concrete in our structures. And this is a problem that we can address through the design and fabrication of structures within architecture. And me as an architect, this is where I want to make a contribution to this field, basically. So we're working together with our colleagues of material science that are advancing new concrete mixtures. But we believe that we can really reduce the amount of concrete that we use for structural buildings and still have similar performance. So this is also not a new idea. So in the 20th century, there were actually already many people that have explored this idea of more structural efficient concrete structures. The only thing that was different at this time is that labor was very cheap and materials were expensive. So it made sense to make, for example, structures such as this beautiful ribbed slab in Germany, because you could reduce the amount of concrete that you use and the amount of steel, although you had a bit more cost for the labor. It was still worth it from an economical perspective. However, if you look at the cost division of this particular structure, this roof, you can see that 80% of the cost was actually made up by the formwork. So not the final materials that go into the structure, not the structural concrete, not the steel, no, just the temporary scaffolding to hold the concrete in place while it cures. So this is really the element that restricts us basically in building these kind of non-standard structures. So what we are doing at ETH Zurich is we are trying to tackle this problem of inefficiencies in formwork by using 3D printing to produce the formwork. And we can do this by combining robotic fused deposition modeling 3D printing with a special type of casting that we've developed at ETH Zurich that's called set-on-demand casting. So set-on-demand casting was developed over an earlier research project at ETH Zurich. And what you can see here is that a column is made with a formwork that is robotically moved up vertically. So you can see that this column is made with a formwork that's much smaller than the actual structure that's being made. And the concrete, it's fed in from the top, and then it hardens quickly. And by the time it exits the material at the bottom, it is already can already sustain its own weight. So this also means that the pressure on the formwork is reduced because it hardens, let's say, within 30 minutes, for example. This is something we can control. Now, how is this related to 3D printing? Well, you can see here some of the very first tests that we did with 3D printed molds. You print a thin mold using a small printer, cast it in the concrete, it breaks because of the pressure of the concrete. However, if we then apply the same strategy, the set-on-demand casting strategy that was used previously for this column, and we cast in the concrete, in this case while the structure is being printed, and it is already hydrating, so the pressure on the formwork is limited, we can actually use these very thin 3D printed molds. Sorry, I just need to... Sorry, let me try to display the video. Okay, anyway, so you can see here that the robotic arm is printing the thin formwork, and then what we do is at the same time we're casting in the concrete. Sorry. Yeah, good. Well, anyway, at the same time we cast in the concrete, and you can see also here that we have, for example, these voids that we leave in that will be used later for reinforcement of the structures. So you can see this is a very thin mold. It's only 1.5 millimeter thin in this case, PETG material. That was printed using its early stages of research, so just our own self-built filament printer. This is then, for example, a structure that was made during this project. This was actually student work, and the students, in this case, they wanted to explore what are really the limitations or the possibilities that we can have using 3D printed formwork. So let's say, how crazy can we go in concrete structures? And I think this results really show something that is, it's almost impossible to come to fabricate in any other way with milled formwork or in any other method. Of course, this is not an optimized structure, right? This is not an efficient way to make a column, but that was not the point of this project. It was more to show how far can we go. So in particular, the objectives of our research are to make it possible to fabricate these kind of material efficient structures in a better way than we have now, so that we can reduce the amount of concrete that we use for structural building components, with the minimization of formwork waste, of course. And as well, we want to integrate steel reinforcement into the concrete structures because this is critical for them to be code compliant and actually applicable in the construction industry. Then there's also another option, another possibility that 3D printing offers to combine multiple building functions in the same element by, for example, leaving voids or these kind of possibilities. So I'll now show a couple of projects that we've been through the years. This is the first project called the Future Tree. It was done for a Swiss engineering firm that wanted to have an extension of their office building. You can see here in the top, you see their office building. They were going to extend it, and they wanted to make some kind of eye-catching canopy in their courtyard. Also a bit as a pilot project for digital planning and digital fabrication technologies. So what we did is we combined two research projects from our group. On the one hand, a timber roof fabricated also with robotic fabrication, so robotically assembled timber roof structure. And on the other hand, a concrete column that was made using 3D printed formwork. So for this column, we had to rethink the fabrication process a little bit. In this case, we did not cast and print cast the concrete and print the formwork at the same time, but instead we kind of went for a more traditional consecutive process, such as is more typical in the construction industry, where the robotic arm prints the formwork, we prefabricate the reinforcement, and then the concrete is cast using the set-on-demand cast concrete. So still slowly filling up the concrete to avoid it from breaking the formwork. So quite a lot of challenges that we had to solve, because this was really the first, let's say, structural application. It also had to be completely code compliant for a real building project. So we had to fix the large-scale 3D printing. At that point, that was not really something back in 2019 that we had completely under control. Integrate reinforcement and really investigate how far can we push the design of the structure. So I just fly over them a bit. In terms of reinforcement, we had to use standard reinforcement. This meant we had to change the shape of the structure a bit to fit an actual reinforcement cage that we could kind of post-place after printing of the formwork. So rationalize the design in that sense. Then in terms of large-scale 3D printing, at this point we were using a filament printer that was just a self-built, quite low-tech extruder. And we were printing it with a diameter of 1 meter, this crown, the sort of top section of the column. And what we found that we had a lot of problems with layer delamination during our first tests. But then we figured out that we could actually apply some kind of patterns on the structure. For example, in this case, a zigzag pattern or more of a diamond pattern. And in this case, we could reduce the delamination because the filament always tries to shrink in the direction of the layer. And in this case, these kind of high stresses, high internal stresses within the layer could be avoided. And we could make it feasible using this particular printing setup that we had. So we tested multiple patterns. We kind of ended up with this diamond pattern that also gave the formwork a little bit more stiffness and is really reflected back into the concrete. So this is then the final design that we came up with. So we had a steel plate on the top and on the bottom to connect to the foundation, the reinforcement cage, also integrated drainage going through the column. And you can see that, for example, the pattern, it is not very visible at the bottom, but it is very visible at the top. This is because in the bottom it was not really needed because this was easy to print because of the small diameter. But at the top this was necessary, so that's why we turned it sort of this sort of fabrication aspect also into an aesthetic feature of the design. So here you can see the column being printed in our lab. So at this moment this still took, I think, 26 hours to print it out of PETG with a layer height of 1 millimeter only and a layer width of 1.5 millimeter. Then put in the prefabricated reinforcement cage and then cast it using set-on-demand casting. So in this case still by hand, manually casting in the concrete layer by layer to avoid it from breaking. Then we peel off the formwork. And then we can also recycle it. This is something that I get back to later. So here you can see the column, the formwork, reinforcement cage and finished column side by side. And this is it then placed on the construction site. So the roof was also fabricated in 5 prefabricated modules, shipped to site, and everything put together as a sort of first example of, okay, we can actually use already 3D printed formwork in a real construction project, adhering to all the required building regulations. So that was an interesting first finding, but then of course what we started with were columns because they were relatively easy to print. These kind of vertical structures, they lend themselves quite well to FDM 3D printing, but it's not really where the material savings are. So in the beginning I said what we actually want to do is we want to reduce the amount of concrete that we need for structural building components, and in terms of columns we have a bit less potential there because they're already efficient at transferring the compressive forces. However, in floor slabs, there's a lot of potential to optimize them. And we wanted to see, okay, can we use a similar printing and kind of fabrication approach to make optimized floor slabs and see how much can we reduce the amount of concrete. So we came up with a design that is inspired by some of the famous designs from the 20th century. Nervi and Hecker and Maillard also have came up with similar ribbed systems that really aim to place structural ribs where you actually need it in terms of flow, force flow of the floor slab, and otherwise in any other place just leave the concrete as thin as possible. So here's a small video that illustrates the process. So you can see here the design. We went from for a situation, kind of an typical office situation where you have an 8 by 8 meter grid of columns. We also developed a digital design to fabrication workflow where we analyzed the forces and then directly generated the formwork and the fabrication data of the optimized slab. So we designed it to be use 40% less concrete than a slab that could have a typical, like a flat slab that would normally span 8 by 8 meters. So here, this is the formwork being printed in our labs. At this point you can also see we scaled up our extruder, so we bought the CEAD extruder, the E25 robot extruder, and this really allowed us to go much bigger, a big scale increase and quality increase as well in related to our kind of self-built previous extruder. So we also integrate the reinforcement into the formwork. and printed, in this case, stiffening ribs that were attached to the formwork to counter the hydrostatic pressure. Because actually here we wanted to use a standard concrete instead of this sort of more fancy, more expensive settle demand concrete that we were using before. Because we wanted to be closer to the real applications in the construction industry and bring down cost as well. So yeah, the formwork was printed. I think it took, in this case, 24 hours to print the entire formwork. And it was cast in 2 casting steps. So you saw before that the ribs were printed. So these are the main structural elements. And then in the second step, we cast the flat slab that's only 8 centimeters thin. And this is just to provide the surface to, in the end, walk on, to provide the floor. You saw also that we made another element, a flat slab, and we compared the two to see, okay, are our assumptions on these 40% material savings, are they indeed valid? And we found that actually we could achieve a similar structural performance with the optimized slab with 40% less material. So our assumptions were sort of validated in this demonstrator, which we also designed to be compliant to building codes again, so it had the proper reinforcement and everything integrated into the building element. Of course, it was still a prototype, and also it was just a single element that we tested. That's why for our most recent project, we worked together with the students from our postgraduate master at ETH. So this is the Master of Advanced Studies in Digital Fabrication. And we gave the 17 postgraduate students, we gave them the task, okay, we have developed this technology over the last 4 years. Now we want to build a real building structure with it. What can you design? What are the designs you can think of to come up with something expressive, innovative, as well as sustainable? So we got a site for this project, which was at the Vitra Museum in the Weil am Rhein in Germany. So on the campus, there's already many examples of very interesting architectural pieces. It's a bit of a playground for architects somehow. Yeah, we were chosen to put the pavilion before the entrance as part of the Hello Robot exhibition. So it's an exhibition about robots in general, in media, in whatever, and we represent sort of the robots in construction in this case. So the students came up with a design concept, and we gave them some constraints, of course, because it was quite a limited, the project was quite limited in time. We only had 3 months to go from initial concept to complete fabrication of all of the building elements with this group of students. So what we told them, gave them as a brief, as an assignment, we said we want a roof structure around 10 to 15 square meters. You can have around 3 cubic meters of concrete that you can use. It should be maximum around 3 meters tall, and it has to be reinforced concrete, again, according to building codes. And we need dry connections between the elements because it needs to be assemblable and disassemblable after the exhibition is finished. So the typology that they came up with, or we came up with, was that we had a sort of a center column and slab pair, and around that 3 satellites, column and slab elements to also ease the assembly on the construction site. So this is the vision that they had for it. So you can see the center column and then a slab element on top, and then 3 other column and slab pairs that were next to it. Again, following this method of having ribs where you need it, and only a very thin 6 centimeter slab in this case to just create the roof. So the students also adopted a computational design workflow to make the shape of the pavilion, where, for example, first you generate the outline of the pavilion, and then you have each slab element. From the slab element, you create from the middle, you create the vectors that go towards the corners. And at this point also the shape can still change, so depending on the angles it becomes either 3 or 4 ribs. And from that then also the bisecting vectors are formed, which then forms the shape of the column. And then the shape of the shape of the column is sort of extruded down to form the capital shape of the roof of the floor slab. And then by defining the rib sections, here in collaboration with our engineers to make sure that everything is structurally feasible for these particular spans, we could then design the structure and the column. and also the reinforcement that went with it in this computational design. So there were still many iterations throughout this whole project, and what's interesting about this parametric workflow is that you can really still change the design right until the moment before production without having to manually redraw the components of the structure. So also, of course, 3D printing allows for creating some interesting patterns. In this case, they were really just more guided by aesthetics and by having extra visual elements connected to the column. And then the geometry, again, like in the ribbed floor slab project, was automatically generated, everything programmed, what kind of distance we need for the stiffening ribs, what sort of height, what sort of spacing, and making the fabrication data. And this then really was a completely functional script that could still change until right the moment before production. Here you can see the technical details of the project. So we had a column cast onto a steel plate that was connected with another steel plate and then put into the ground with earth screws, which is a more reversible foundation method. And then it's connected to the roof with threaded rods that stick from the column through to the floor slab. So we created 4 columns, 4 slabs, each a little bit different. And also what we did for this project is we recycled formwork from a previous project. So it's something that I said before. Throughout the project we always said this is a possibility with 3D printed formwork. But now what we actually did is we took formwork from an old project where we made some furniture actually from concrete. We cleaned it a little bit, the formwork that we took off. We shredded it to granulate, then regranulated it, and then 3D printed the regranulated material. So the columns of the formwork columns were printed fully from 100% recycled formworks from this previous furniture project. So this is a little video that shows a bit the design and fabrication process. This is what you saw before, the computational design generation of the structure. So the students first started prototyping in a bit smaller scale with our small extruders to create the shape of the columns. Of course, many tests were also done. What we also integrated in this project was actually automatic casting of concrete. You remember in the first project I showed, the future tree, we actually cast the concrete by hand, but at this point we automated it. Here you can see again our gantry setup in the lab, printing the formworks. So these are completely recycled, printing the 4-column formworks. So each column was printed in around 6 or 7 hours. They were 3 meters tall or 2.8 meters tall. Again, insert the regular reinforcement. So we had 2 different strategies. On the one hand, we cast the columns with our set-on-demand casting strategy, but in this case we automated it. So you can see here we have another robotic arm that's used with a funnel attachment where accelerating admixtures flow in. So these are the admixtures that make the concrete harden quickly at exactly the time that we need it not to burst the formwork. And this setup can then be used to automatically fill the columns in 1 hour, whereas for a previous project it still took 6 hours to fill the columns because of the hydration of the concrete. For the floor slabs we had a similar strategy to the rib project that I showed before. Prefabricated reinforcement cages were inserted, and then we had to use some non-planar strategies as well to create the ribs, the cap of the ribs to make it possible to print that part. Again, they were fabricated upside down, taking 2 casting steps. And this is then some of the assembly on site at the Vitra Museum. So you see steel plates, columns being placed on the steel plates with a bit of room for adjustment. And you can see the threaded rods sticking out of the columns. That's where the floor slabs will then go on top of. So first placing the center slab, and the ribs of the columns, they sort of of the floor slabs, they sort of transition into the ribs of the columns, with then this as a final result that sort of shows the application again of 3D printed formwork in a construction project, of course still on a pavilion scale, but what we hope to say with this is that 3D printed formwork is actually already possible to use in the construction industry. We can already use it for design, to produce structures that are compliant to all of the existing codes and building norms, and we are very happy to also do more projects and really implement this technology in a real construction project instead of in a pavilion, because I think that's where now the next step is. That's where the technology basically needs to go to transition to a more sustainable building culture with concrete. So thank you for your attention.